We've used the variation method to look at the bonding in butadiene. We call that the molecular orbital treatment also, using the Huckel approximations. Here let's look at water, and we won't make the Huckel approximations. In fact, what we'll do is we'll solve the Schrodinger equation using a computational chemistry program. What we've mentioned before is that the basis set, in contrast to, say, the Huckel molecular orbital theory, where you use atomic orbitals as basis set functions, here for computational chemistry programs, one uses Gaussian basis sets. So just to refresh our memory, we're going to have a trial wave function as the sum over various values here of the combination of this basis set here. It's a linear combination, and in the variation treatment we vary these combination coefficients to get the best wave function, defined as the combination that gives you a minimum energy. So for computational programs, the basis set is our Gaussian functions. And let me write the Gaussian functions as this. I'll use A for coefficients: A1 e to the minus x minus a2 squared divided by 2a3 squared plus a4. That's a general equation for a Gaussian 1, 2, 3, 4 parameters. All right, so that's what we're going to use for the basis set in a computational chemistry program. And we're going to contrast the orbitals we get out. We're going to use the Hartree-Fock self-consistent field method. We're going to contrast the orbitals we get from that with the orbitals that we would get if we use the valence bond picture. All right, the computational chemistry program I'm going to use is HyperChem. So let's go ahead and build the water molecule. Okay, that's an oxygen, so we'll put an oxygen right there. And now we'll tell HyperChem it's smart enough to know how many hydrogens to add. So this is the water molecule, and there's oxygen, and there's the hydrogens there. Okay, so let's do chemistry Hartree-Fock. That's called ab initio in HyperChem. And this is the number of Gaussian basis sets and their kind. What we're going to use a large Gaussian basis set. This is, I forget how many this is, 6, 3, 1, 6, plus maybe 7 or 8 for each atom. So we have a total of perhaps on the order of 15 to 20 Gaussian functions for the water molecule. All right, so let's go ahead and compute that given this geometry. That's called single point. Okay, we're done with the calculation. Let's now see if we can compute some sort of orbitals. Okay, so we'll compute some orbitals. And here, let's just plot the orbital itself so we can see positive and negative. We won't plot the orbital squared. This is the orbitals we have. We have a low energy here, and then we have some higher energies all the way up here. All right, so let's plot the orbital here and see what that looks like. There it is. Looks like this is not going to be a bonding orbital. Looks like all the electron density is centered around the oxygen atom. That's what Hartree-Fock gives for the orbital corresponding to the lowest energy. Let's look at the next higher energy here. Okay, there it is. We'll plot this one. There's that. It looks like this is a bonding orbital, but in contrast to valence bond theory, where you have just electron density here and here, the electron density, the wave function, is all over the molecule, and that's why they call it a molecular orbital. Okay, let's keep on going here. Let's look at the next higher one. Okay, well, that's interesting. So there it is. Looks like this is constant. The electron, this is one orbital, by the way, and electron density is concentrated along this bond and this bond. So one wave function is looking along these two bonds simultaneously, in contrast to the valence bond theory, where you have one bond here and one bond here. This in molecular orbital Hartree-Fock is just a single orbital. Also notice that in this region, it changes sign when going over this region. This, say, is positive, and this then would be negative. All right, let's keep on going up the ladder here. Let's look at the next one. There's another one. Well, that's an odd kind of orbital. You have some electron density here, and you have some electron density here. but it's not clear whether this is a bonding one or not. But it is, in the Hartree-Fock treatment, an orbital, a wave function, and it's a molecular orbital, extends over the entire molecule. Let's go up one further here, plot this one. There's that one. Well, there's an interesting one. So there, the electron density, this molecular orbital, is over the entire molecule also, and it doesn't change sign. If you want to make an analogy, or maybe it does change sign. Yeah, well, let's take a closer look. Let's take a closer look. Oh, look at that. Oh, we were fooled. So yes, it does change sign. In fact, it's just like that other one, except it looks like it's rotated 90 degrees. Now, if you're going to say this is something, well, perhaps this is, say, the atomic P, or a non-bonding pair of electrons on the oxygen, is occupying this orbital. All right, and then let's keep computing here. Let's do the highest occupied orbital. Well, that is the highest occupied orbital. Now let's go above that, and now we're in uncharted territory. If we plot this, well, that's an odd thing. And that's the danger of just using computational chemistry programs just willy-nilly, because then you say, oh my goodness, look at this. This is the first the first unoccupied molecular orbital. And you're saying, oh my goodness, this must mean something. Well, actually it doesn't. In the Hartree-Fock computer programs, what you do is you optimize only orbitals that have electrons in them. So these unoccupied molecular orbitals in the simple Hartree-Fock treatment don't have electrons in them, so they're not optimized. There are techniques where you can optimize those orbitals that don't have electrons in them. But for now, the way we did it, we just have to consider the bonding orbitals, or the orbitals that have electrons in them, which may or may not be bonding depending on how you look at things. All right, so that's in a nutshell how one does this Hartree-Fock computational stuff with a computational chemistry program. Okay, and so what I hope to convince you there is that in the valence bond theory, you have in a water molecule, for example, you would have an orbital coming out here, and then here's hydrogen, this is oxygen, and you have an orbital coming out here, and you have an overlap, and that's one bond. And then in the valence bond theory, you have another orbital coming out of oxygen, here's a hydrogen coming out, this orbital overlaps, and that's another bond. But when you talk about molecular orbitals, you no longer have these localized bonds. In fact, orbitals now, or wave functions, are over the entire molecule. In fact, what we could do is describe more clearly what the valence bond picture is here using hybridization. All right, so let's describe the bonding in water in terms of there's a bond there and a bond there. So valence bond theory in the normal chemical picture in introductory chemistry is you have a bond to this and you have a bond to this. But if you do the Hartree-Fock molecular orbital stuff, then you no longer have these well-defined bonds. You can modify the computational stuff and combine various orbitals to get the more likely the chemist picture, but just for a first approximation, those Hartree-Fock orbitals are molecular orbitals. All right, so what would you say this is? This would be sp3 hybridization. Why is that? Well, what you have to do is you have to get the structure. So if we draw these non-bonding pair of electrons here, there's 1, 2, 3, 4. There's 4 electron pairs. And by the valence shell electron repulsion model, this means you have tetrahedral structure where this pair of electrons, that pair of electrons, that pair of electrons, and that pair of electrons point to the corner of a tetrahedral. The molecular structure, of course, is bent, but when you do the valence bond Vesper model, valence shell electron pair repulsion model, you have to consider both bonding and non-bonding electrons. All right, so if you have tetrahedral structure, then this implies you have sp3 hybridization. Okay, sp3 hybridization. So in fact, that's how you have to get the structure, and then you get the hybridization. That's essentially what Linus Pauling did in the 1930s, sort of post facto justification. So now you have an sp3 hybrid up here, an sp3 hybrid, sp3 hybrid, sp3 hybrid. All right. And then here you have the atomic 1s. So this bond would be an overlap of an atomic 1s on hydrogen with a hybrid sp3 on oxygen. And the same way with this is the hydrogen 1s. You have bonding there. And so that is what that is also. All right. Now that's in contrast to molecular orbital theory, where in molecular orbital theory, you just have an oxygen, you have a hydrogen, and you have a hydrogen. And you fix the position by the Born-Oppenheimer approximation. You fix the position here. And then what you do is pour in electrons. How many electrons do we have to pour in? We have to pour in 8 for the oxygen, plus 1 for the hydrogen and 1 for the hydrogen. So that's a total of 10 electrons. So the system that the Schrödinger equation describes is 3 fixed nuclei, an oxygen and 2 hydrogens, plus 10 electrons. And then you say, okay, what sort of molecular orbitals can you get which will satisfy the Schrödinger equation? And those molecular orbitals were attained by some sort of variation and combination of Gaussian functions in computational chemistry programs using Hartree-Fock. We'll talk a little later about orbitals and why I think that orbitals are figments of the chemist's imagination.